Good evening, we're here yet again to do another one of these bonkers builds from Erica Synths. I'm, as ever, fully prepared, ready to go, having studied hard all day. You don't believe a word of it. No, I know. Yes, I just about made it, I think. Sorry about the slightly less than prompt start. Busy, things to do, places to go, kids to take about the place, tea to cook, that kind of thing. Anyway, we are here, so welcome. You're very welcome. Hi, Moog Lee. I guess I'm having to say. Steve, Ken, good to see you. Corey, and that's me. Good to see me in there too. That's great. We're all very, very welcome to be here this evening. This evening is the build of the Erica Synths EDU DIY mixer. Now, somewhere in my head, I am assuming that this is a quick, easy, short one. But that's never been the case, and just glancing over at the manual, I note that it's 48 pages. So, heck, there's no point sitting here chatting then as much as I'd like to. We'd probably just better get right on with it. So, okay, I might need to... Oh, oh, we're not... Oh, let me... I'm just going to have to organise my space a little bit more because I'm crowded. Now this here, I don't think we're going to be using this quite yet. What is that doing there? See, that's my spot for this. I don't know. Oh look, this can just go over here for a minute. Perfect. So the mixer, that's what we're looking at. Now this is hilariously didn't actually come. What is this? Didn't come in my box that came from Erica Synths with all the other modules in it. It turns out that I've got two sample and hold modules, which is fascinating, instead of having one of those and one of these. So I picked this up from Thonk last week. Thank you very much for sending it out to me. By that I don't mean that they sent it to me for free. I purchased the thing. So this one has not got paid promotion in it. I pay for it myself. The mic is cutting out, is it? Oh, is... 1, 2. Well, I mean, it looks good from where I am. Is that everyone's experience? I mean, I don't have a noise gate attached to it. Flipping crows going now. Can you hear that all right? I will bring the mic a little bit closer to me because other people were complaining about it last time. Although, you know, I've been playing it back. Didn't seem too bad. Anyway, still adjusting. See if I can get myself sorted. Is that better? Do let me know if it's better or worse or that kind of thing. Sounds good. Great. Okay. So yeah, the mixer. So let me get the right sort of thing going. Is that the right sort of thing? Yeah, let me do that. So the plan with these sorts of evenings is to build out the module onto a breadboard like this, and to see whether we can get the thing to work, to see whether we can understand how the mixer works, how the circuits work, what it is in the component choices that actually makes the mixer a mixer. And not only that, it has a diode based distortion inside, which is particularly interesting, I think, for this build, because otherwise a mixer is fairly run-of-the-mill, I would have said. So it's good to have something else in there as well. So let's crack open the box and just have a quick look before we get the components out. I mean, I am getting the components out, obviously, but before I tip them out, let's just have a brief look. There's a bunch of stuff. It's not looking that hard, is it? Look, and there's a bunch of hardware. That's hardly anything at all. Hardly anything. That's great. So the way this tends to go is that we do the breadboard build out on one night. Oh, for crying out loud. The cockerel. It was your end, definitely, Mr. Moog. What the heck is that? This is going to be get out of it, an evening of accidental wildlife encounters. So this is the front panel, mixer, or maybe under here now is a better place for it. And this is the PCB. This is easy. We could do this in our sleep, this one. But we're not going to need those two bits, so we'll put those away for now. We're going to be more interested in these other two bags as we build the thing out on our breadboard. Right. Okay. I need this a little bit smaller. Let's get rid of the keyboard off my surface. Oh, stuck to it. Lovely. All right, doing all right out there. That's good. Glad to hear it. Waiting for the answer. This right. Am I sorted yet? Right, so let's have a look at this here manual to see where we get to. Right. So I will just crack on, otherwise time just disappears. So lots of pleasantries. Hello, glad you could make it. Wonderful to see you. Let's, what are you looking at? You're looking at it from down. Let's have a look at the manual, which is this one. Smooth as silk and all that. I should have some kind of preview up here, shouldn't I? That would help me. Let me do that. But I'm not going to see that for minutes, so why am I even trying to do that? That's ridiculous. No, forget that. Forget that. Oh, if I seem slightly off today, it's because I'm all over the place. So, anyway, let's have a look at the first part of the manual, the mixer. So it may be a bit of a utility function in the modular synthesizer, but it doesn't mean it has to be dull and boring. Well, there you go, yeah. See, I don't know what I'm talking about. This super simple 3-channel mixer has a built-in diode distortion that Moritz Klein has designed that will make your patches sound delightfully rough. Well, that sounds interesting. That does sound interesting. Now here is our circuit diagram. We have, I should get a mouse working so I can point at things. Is this working just like that? It is, flipping is, look at that. So look, we've got a bunch of variable type resistors. We can spot those now, 100k ones. We've then got some kind of some kind of op amp thing in the middle here, which then goes to another one over here, look, which then goes down over a little bridge, which is nice, down to, oh look, a couple of diode things, and another op amp doing some stuff. So that's exciting. Looks like we get an output and an inverted output, useful for mixing CV. That's it. Really, really, really simple. So I think all I need is the one of these. How am I doing this these days? Where have all my little ones gone? Where do they exist? There. Okay. Because I graduated onto these new bits. I'm going to need my batteries. Hang on, I'm still just getting myself together. 2 battery headers. Right, good. Okay, got that. Don't need the rest of that. That can sit up there in my Deckard's Dream junk pile. Good, bunch of those. I'll need some pincers, probably my other pair. Good, lovely. This is what was left over from last time. Anyway, moving on. Got our circuit diagram. Bill of materials. Let's check that we have the bits that we need. Okay, sadly I didn't do this beforehand, so I'm going to need to do it now, which is the measuring and labeling of a bunch of bits and pieces. So we have, chips are easy to identify because they sit there looking like chips. So there's some resistors, some diodes. Bring this down so you can see it properly. Some of those, those. Come on. Okay, good. So we should have 8 100k. So I'm going to go with this. These here being the 100k. Now a pen would be good at this point. Lovely pen here from AJH Synth. Look at that. So these are 100k. I could measure them, of course I could, but not going to, because you know, as far as the bill of materials is concerned, there's one pack of 8, so that's going to be these. So I'm fairly confident that those are the 100k ones. Then there's going to be 3 1k, which are these. I mean, if I look with my glasses, I can see that this is all browns and blacks, and browns and blacks is always 1000 something or other. The same as this is all, well, brown, black, and then orange. So that's nonsense, obviously. Don't mind me. Anyway, those are 1k. I'm going to go with that assumption. Then I've got 2 10 ohms, and oh, I've got different ones left here. That's interesting. So what do I have? Do I have an extra? I've got 3 1k, 8 100s. I should have 127 and 2 10 ohm. Well, at this point I'm going to have to measure them, aren't I? Just to be sure. Are you all still out there? No one said anything for a while, and that always just makes me nervous. So, you know, give us a wave. Let me know that this is all still happening and I'm not just talking to myself like an idiot. So, checking these. What you got to do is stick your crocodile clips on either side. Stick it onto ohms and it should tell you what's going on. Okay, so that's 26.8, which we'll call 27, shall we? So that's the 27. It's hardly worth it. Okay, thanks still, Steve. And Christ. I don't know. I'll save you. Thanks for the wave, Ken. That makes me feel so much better. What did I do? I got the 27. So I've got these 2 and the other ones. That is nothing at all. Okay, here we go. What are we expecting? We're expecting 10 ohms. At the moment I got 16, then I had 34. What is going on? What is going on? Wait, maybe these are something else. Oh, these are something else. These are not what I think they are. That's why. See, if you look at these closely, don't know if you can look at these closely. No, let's not do that. Let's just put those here. These are not flipping resistors, or if they are, there's something else. They just have one black stripe and they look like sort of dumbbells. Interesting. These must be... I have no clue what they are. There's no mention of such things, unless they're diodes. But I've got diodes. All right, so those are weird. Let's put those to one side for the minute. So this must mean that these are our 10 ohm. I mean, you know, any clues in the comments, please do let me know if you know what on earth they are. Come on, be 10 ohms. There you go, there you go. There you go, well done, 10 ohms, good. Right, sorted all those then. And just very, very coolly, I'm going to let the weirdo ones just pass me by as if I don't have a care in the world. Good, so that's the resistors. Then the capacitors, we've got these 104s here, these drippy ones, of which there are 6, which is great, and 2 electrolytics, which are these fellas here, which we do have. Some diodes. Told you this is easy peasy. And then a bunch of pots and trimmers and jack sockets and a couple of chips. Rock and roll. Let's get on with it then. Okay, so we've got all this fuss overpowering my breadboard, which is always a bit of a struggle every time, but we seem to get it done in the end. Now the manual gives you instructions on how exactly to do all this. Put this up here a little bit. But essentially what you're doing is combining these two 9-volt batteries to provide a kind of a fake Eurorack supply. And unfortunately my breadboard is upside down or backwards compared to the one that's in the manual. So I have to just make some slight leaps in when I put it together. But what I want to do is follow not the labeling, but the positioning of things. So I know that with one battery, the positive goes on this inner bit there. And I know that the negative goes on the outside. And that's connected to the positive of this battery, which is going to go there, and the negative goes on the outside. So essentially what you get is ground on that top edge and ground on this top edge. You get positive plus voltage 9 volts on that inside edge and negative on this bottom bit here. And so when we're following the breadboard diagrams in the manual, it's important where those things end up. All right? Good. So now that I've set that up, I'm going to take it apart so that I don't kill myself or, you know, blow things up. I've got a bunch of these things which are all in the way, which are going to need to come out. And I think that's all the prep, and we are ready to mix. I need to find 3 sources from somewhere. That's going to be the next thing. Right. Good. So what are you looking at? You're looking at that. I'm going to bring that in a little bit so we can see it a bit clearer. And let's have a look at our basics. So before we talk about the circuit design, let me get more comfortable. You need to understand what a mixer does. Thankfully, compared to other types of modules like oscillators, filters and VCAs, it's pretty straightforward. Got one purpose: to mix signals together. Yeah, I think we get it. I think we get it. Oh, nice, Ken. That's interesting. A breadboard power unit. Cool. I mean, is that enough to run the stuff that we're doing? I've no clue. But it's good. So the result, so you've got one purpose, which is to take input signals and mix them together. The result should be made available via a single output. And ideally we want level control over each. That's what we're after. So a passive mixer. To start out, we'll look at the simplest mixing circuit imaginable. 2 resistors connected together, side by side. Send in your 2 signals, and you've got a mix. So I'm going to need signals all the time, aren't I? For this. how am I going to do that? So I've got, well, I've got two outputs on the VCO that I could use for a bit of waveform mixing. Ideally I need 3, don't I, thinking about this. Do I have anything else to hand which has anything useful on it? Just a second, let me think. Bum ba bum bum bum. Something with enough waveforms. Alright, just hang on a sec, I'm just going to rescue an oscillator from somewhere. Doing. Okay, I'm going to take that out of there, turn that on, I'll need that for testing purposes. I might be getting ahead of myself a little bit, but you know, it'd be good to have some form of sound source. I think would be really good at this point. Oh, it's too big. Well, let's stick it over here then. There we go. Excellent. Excellent. Can't see. It's a disaster. What am I doing? Now, where was the power for that? I've got 2 powers here. This is the nifty case one. Look at that. This is this one. There's no cause for alarm. Super. Right, I'm going to have that sitting there for now. That's just wavering a little bit, but that's okay. Nothing bad could possibly happen. Go on, screw in. No, not doing it. Right, great. So what we're doing, so yeah, right, okay, so basic mixing. So I've got myself a sound source now, which I can use in a minute. Of course, I'm using the Look Mum No Computer 1222 Performance VCO as per my very recent review, and that's going to provide us with some waveforms that we can mix. So let's have a look at what we've got to do. So the most basic mixer just uses a resistor. The 2 resistors taken together form a voltage divider, which might sound somewhat confusing at first. I am all over the place. Okay. Usually you see voltage dividers being set up like this. Yes, we've seen this before. The resistor and then a resistor going to ground, a voltage divider, which then changes the voltage from on the input to the output. It, you know, that it divides down the voltage. We've seen that. One resistor connected to a reference voltage and the other connected to ground. If both resistors are the same, you pick up half of the reference voltage in the middle between them. In our setup above, confusingly, both resistors are connected to reference voltages. This one they must be talking about, the next one, okay. Both resistors are connected to reference voltages, which also change over time. Since we're dealing with oscillations here, can we even call that a voltage divider then? Okay, so we're talking about these two here. They've both got reference voltages because these waveforms are essentially voltages which are changing over time. Got it. So yes, if we simply freeze time at any moment, we will see something like this. Two fixed input voltages and a fixed output voltage. Now, of course, either of these input voltages may or may not sit at ground level, but for a voltage divider, it's mostly irrelevant what the two input voltages are exactly. What matters is the difference between the two inputs, which is what the divider is operating on. Since both resistors in our divider are the same value, the 4-volt difference will be slashed in half and the result gets added to the lower of the two input voltages, giving us a 3-volt output. So we're now looking at this thing here, 5-volt going in, 1-volt going in. This is frozen in time. This is our basic passive mixer from up here. So what we get, the 4-volt difference, okay, the difference between the two will be slashed in half, giving 2, and that's added to the lowest of the two input voltages, giving 3. The grounded voltage divider does exactly the same thing if you think about it. It slashes the difference between our reference voltages and ground in half and then adds it to the lower of the two input voltages, which happens up here. You've got 4 volts, excuse me. You've got the difference between the two, 4 volts and the 0 volts essentially, which gives you 4 volts, and then that's taken in half, that gives you 2 volts, and then is added to the 1 volt, which gives you 2 volts still. I think. Got it? Good. Right. So it looks like we're going to do some of this. Because our operation stays the same regardless of what exact input voltages are, the output would always be the midpoint between them. That's why the setup above works as a mixer. It simply puts out the average of our input signals. Right. To try this in practice, let's do it on the breadboard. Hurrah! Okay, let's do that then. So looking down from above, what we got to do. So we're going to need our patch sockets for that. Patch socket's always a pain on breadboards, I think. I'm almost inclined to wire, to solder bits of wire onto them just to make it easier. But, you know, when it sits right, it's beautiful, but it doesn't always do that. So up here at around 50, one before 50, and on the edge of things, this is going in. Just stick that front edge in, and it should sit nicely. There's another one going behind it. Am I doing this right? No, not in the slightest. That's good then. That looks like that's going right up its butt there. Nice and close. Okay, that's those two done. We then want a wire which is going to take it to ground, which is the top bit. I need to go from there to ground. That's not right. It's going to be one of those nights, I think. Right, let's try and take something that's a bit more the right size. See, I find once you've used these little bits of wire, they then become useless because they're all misshapen never quite fitting in where you want. I liked my long cables, but I'm going to persevere with this because I'm told this is the better way to do it. I like to do what I'm told, as you well know. I respond well to suggestions. Okay, so that's one's in. So it's just taking the earth from that leg there to the ground. That's what that's doing. I then need another wire, which is going to go, needs to be a bit longer than that one. Take this green one. Is that going to be too long? Oh, that might work. So the green one is also going from ground to the ground of the one behind. Yeah, that is too big. Let's find something else. These red ones look perfect. Oh. So we are going from ground to ground. Like that. I'm going to need my magnifiers on so I can see what I'm doing. Ground to ground, good. See that all right? The camera's different. Trying to work out what it is that I've done different. So I've had things all over the place. Maybe if I bring it round a little bit, it'll be a bit more on the top. I'm just always worried about getting my head in the way. Is that slightly better? And let's just say that it is. Okay, then we need to jump the void between, going from the back pin just over the bridge. This is slightly too big. See, I would have expected something to be exactly right for going over this middle bit. So it's going from, yeah, these blue ones. Where's it going from? The back of that into there. I love these. I love them. Thank you so much for making me use them. Okay. Out. Good, good. There's probably a tool, isn't there, which puts these in. There's probably this, but there's probably another tool that does it better that I'm going to have to get as well. Right, so that's gone in, and then there's another one at the end of this one here doing exactly the same. Oh, that's easy. That one was easy. Did you see that? Right, good. So that's the easy stuff, and I'm taking far too long about it all. Then we need 200k resistors, which I've got here. Okay, they all both start in the same place. They end up different. So from there, 1, 2, 3. So from here, 1, 2, 3, there. And there. This one goes to that first wire. This one to the second. So these are our inputs, presumably, our two inputs here, which are then, each one is going through a 100k resistor. Yeah, 100k resistor, both are inputs. So our inputs are creating voltages, the voltages are going through this voltage divider of the 100k resistors, and that's going to our output. So our output sits over here. On the almost 30 mark, like that. And a little wire just to go over a couple. So this needs to go to the back end of this, to that resistor. That's right. Come on. Come on. So resistor. To there. Good. And then just need ground to go to ground. Bloody things. Alright, I'm going to assume that all went in all right. Okay, good. You following me so far? So voltages come in. They are grounded. Grounded. Then the signal comes through 100k, through 100k, and then goes out the other side. That's it. I mean, there's nothing else going on. That's it. So I can use a regular audio signal, apparently, coming from an oscillator or your phone or a drum machine. That's exciting. Right, so I'm going to need an output. And something nice and long. That's not long enough. This one. That'll do. Plug that in over here. There's some kind of noise coming through that, I think. Okay. I apologise for any overloading of speakers as I plug this in until I get the level about right. So let me turn that down. I'll just plug this into the output of one of these. You like that? Okay. Good. So this is going to be plugged in to our output here. And then from this fella, I need, oops, a couple of longish cables. That'll do. Do I have another really long one? So take the output from the square wave, plug that into one. I could take the output of the other VCO over here. Plug that in. Oh yeah, it's all happening now. Yeah, so we're mixing. Sorry, I won't get carried away by the easy bit. So there we go, two inputs mixed together, coming out of the output. Fantastic. Great. We could do this all day. I mean, is that essentially what you get in a mulch? No, that's not what a mulch does, is it? The opposite. Alright, no, don't get distracted by that kind of happens. So good, look, there you go, great. We did that. And I did it because it's passive. It didn't even need any power because I'd forgotten to plug the batteries in. So it just works. Great. Great. So it mentions how it wouldn't be very loud. I mean, I'm running it through a Eurorack system, so it's used to having hot signals, and that's all fine. If you're using, it says if you're using something else, you might find because it's passive that it's going to be very low. So it doesn't amplify the signal. The two resistors strongly limit the amount of current that will reach and drive your headphones if you're using headphones. So what they say is that this circuit has really high output impedance. That's interesting. Hey, thanks. Thanks, mate. That's just delicious of you. Thank you very much indeed. How nice. How nice. And look, it's 8:20 and I haven't got anywhere. But thank you. That's very much appreciated. Mr. MW Mac. So, a simple active mixer. Now we have to start talking about op amps. Oh, it's going to get hard now. So to fix the amplifier thing, we need an op amp, you know, an operational amplifier, something that amplifies signals. Yes, of course, that's what we're going to need. Let's bring us to the manual. So we need to set up an op amp, a buffer between the two resistors and output socket. A buffer, if you don't know, basically provides a copy. It's this weird copying thing that it does. It's quite extraordinary, really. I'm totally amazed by how electronics works most of the time. So basically it just provides a copy of the voltage you apply to it without putting any current into its input. This way we can reduce the output impedance, drastically, because the buffer is able to drive our headphones directly. Great! Still, we don't want the output impedance to be 0, because that would make our op amp vulnerable to short circuits, if you say so. So we'll put a 1K resistor between our buffer and the output. This is low enough for the resistance to drive our headphones, but high enough to limit the current output flowing to safe amounts in case of short. For the op amp, we'll be using the TL072, which is 2 op amps in a single chip. Make sure you set it up exactly here, or the whole thing will explode and it will be bedlam. Right, let's unplug these for the moment. Now, because the system sounded all right to start with, we're probably not going to appreciate the amplification of this, but let's go through this anyway. So, does everything stay the same? So we've got this bit here, goes to the thing, that's goes to there, that goes to there, that goes across, that goes across. Yes, good, that's all the same. This is not, this is different, so let's pull those out. This is going to move away a little bit. Take that out. Okay, so we want one of our little chips. This way up, and this is going on line 36. Ooh, I need to give it a little squeeze with my fabulous squeezing leg tool. Oh yes. So make sure you get it the right way round. Where the dot is, this is going on 36, I believe. Yeah. Squash that in. Good. I've then got, I want to take this signal just up to that other signal. Like so. And then, maybe a grey one in that case. This needs to go up to 35. Just about. Yeah. So then I've got one of my hundreds. It's going to go from this end of this signal and is going to go into pin 2 on this side. The other 100 is going to go from the end of there to the same place. So they are connected, aren't they? If we go back up to here, they do connect together, our two inputs on the mixer, in the manual. So we've got on here both of the 100Ks bringing the signal in from the inputs are going to this pin number 2 on the right. Pin numbering, I haven't got that correct. Don't get hung up on my pin numbering. I'm just looking at it and calling that pin number 2. What looks like a face? From what does? From oh, what? Here. Yeah, it does. Well spotted, Ken. So what am I doing? So yeah, so that was all going into that particular pin on that particular IC, and they need a little one to bring together pins 3 and 4 down this side. Which I think is done like that. I then need a 1K, although there's a, need to jump the bridge here a second. So I need to make sure, oh, it's going to go all the way to the negative, so I'm going to need a slightly larger one. Let's take a grey one. So that pin 1 here, going to go to the outer down here, which is the negative rail. That's good. And I've got one on the other side going to the positive rail from this end pin. Good. They need a 1K resistor, which is one of these. Which is attached also to this end pin in there, and this is going down to 27. Let's not get these resistors to short each other. I then need the output. So that 1K is going to the signal on that, and that needs to go to ground. There. Right, I think that's that. So I've got that 100K, 100K. Got the 1 to 2 there. That's all going into that one there. That's from there. That's from that one. Those two are still connected, and that's going to the positive rail. So if you send in the same two input signals and check the output through the headphones, it should be boosted back up. There's another volume related issue. We'll get to that in a minute. So we've just introduced the op amp, which is giving us this opportunity to amplify the signal a little bit. That's dictated by the 1K resistor. So let's plug that in, and just to see if we get a hotter signal coming through. Sorry if this does anything to your end of things. Now, the thing that I didn't do was plug it in, so I need to put my positives back in, which go, this side goes there, and this side goes there. Good. Now I have no idea whether that did what it said it did, but let's assume that it did. So that has provided a boost for our signal using this op amp and 1K resistor. Super duper. Take my positives out again, just in case. So let's see what the other problem is. So remember how we said that our voltage divider is creating an average of its two inputs. While this does work as a mixing technique, it has a noticeable downside in that the two input signals are always interacting in the mix. Okay. Here's an example. Imagine that signal 1 is currently active. We're getting a triangle oscillation at full volume. At the same time, signal 2 is silent, so the input is sitting at 0 volts. Since our mixer is creating an average, the output will be a triangle oscillation at half volume. Oh, I see. You can test this if we like. I don't think we need to test volume at the moment, because that's not something that's helpful to us just now, but you should be able to hear the difference. But we'll take it as read that we understand what you're saying. No, I could do it, couldn't I? Oh, just do it. Stop trying to get out of stuff. Well, you got somewhere to be. All right, so if I was to, what we want to do is, so we take a single, I know, is that gonna work? All right, let me just plug one thing in. Okay, we get that. Then if I plug this, can you remember how loud it was? Plug this directly into here. Should be louder. Just perfection. Alright, did you get all of that? I'm not sure that we're really experiencing that, but if you are at home, that's awesome. But I understand the idea that's trying to be put across with this. So, how do we achieve whatever it is we want to achieve? What do we want to achieve? You'd expect a mixer to give you the oscillation at full volume, and the state of the other signal shouldn't matter. So how do we do that? We do that with an inverting mixer. So instead of creating an average of our inputs, we need to add them together. Right, so we're not taking an average, we want a total. So that the oscillation plus silence equals oscillation, unaltered. To get there, we have to take a slightly confusing detour through turning our regular buffer into an inverting buffer. To do that, we set up an op amp like this. How exciting. The jumper between output and inverting input gets replaced with a 100k resistor. Jumper between output and inverting input. There. So what did we have before? Oops. We had nothing. We just had a cable. That's what that little plug thing is there. That's taking the output. Yes, that's right. That's taking the output. That's the output going to the signal, to the thing. So we're taking that and putting it back into the inverting input on that third pin, or second pin, depending which way you're looking at it. That's what's going on. Okay. So to make it invert, we need to stick 100k in that place. And we tie the non-inverting to ground. Then we connect our two input resistors to an inverting input. What does this do and why does it help? Well, it causes our output signal to be inverted, so the output will be flipped on its head. In isolation, this seems like a random and useless change, but doing this comes with sort of a hidden benefit, which becomes apparent once we understand how the circuit works as a whole. Oh, that's never going to happen. To simplify things, let me give you the manual. Simplify things, we'll again assume that our two input voltages are static, 5 and 0. Now, since we've tied the op-amp's non-inverted input to ground, the output voltage can only stabilise if the voltage at the inverting input is nearly 0 as well. Oh, this always melts my brain, this bit. So since the op-amp's non-inverting input is turned to ground, the output can only stabilise if the voltage at the inverting input is nearly 0 as well. This is because the output voltage depends on the two input voltages. Right. An op-amp is a differential amplifier, which means that it amplifies the difference in voltage between its two input terminals. To do that, it subtracts the voltage measured at its inverting input from the voltage at the non-inverting input. I wish they had easier names. The result gets multiplied by the op-amp's gain, which is a very large number. Then the op-amp circuit tries to set its voltage to the result. If it's outside the voltage range, it will settle for the last possible value. This is where we get the maximum value, the 12-volt value, all the time. This simple relation gets complicated by the fact that we connect the output of the inverting input through a resistor, because then, if the output voltage changes, the input voltage will be affected as well, which in turn affects the output voltage, which again affects the input voltage, and so on. Bleeding heck. We call this a feedback loop. Yes, okay. And ensures that the voltage at the inverting input is always very close to zero, because if it isn't, the output voltage will adjust until it is. Okay. The feedback loop forces the whole process into a stable state, so it's constantly trying to return to zero. Whenever the voltage at the inverting input is significantly above naught, the result of the subtraction will be negative. Amplify this by a huge gain and the output is crashing down to the negative supply voltage. At the same time, if the voltage at the inverting input is significantly below zero, the result of the subtraction will be positive. You've taken away a negative, so the output jumps up to the positive supply voltage. This means that whenever the voltage at the inverting input tries to go above zero, the output pushes it back down. If it tries to go below zero, the output pulls it back up. They're locked in a stalemate. Now, because of this, we say that the inverting input is a virtual ground node. Oh, do we? Simply because it behaves like a connection to ground, always sitting at zero without actually being one. So when is this helpful? So why is this important or helpful for our problem? Well, let's look at the rest of our example again. Now we know the voltages of these 3 points. 5 volts at one input, 0 at another, and 0 at the inverting input. Why is it 0 at the inverting input? Given these three values, we can deduct that the op-amp's output will have to... Given these three values, we can deduct what the op-amp's output voltage will have to be. In order to get the voltage at the inverting input down to zero, okay, that's what we're trying to do, I think, the output has to neutralise the current flowing through the two input resistors. Since one signal is sitting at 0, though, there's nothing coming in on that pathway anyway, so we have to worry about the other one. The relation is really simple. Our output has to pull exactly as much current through the feedback resistor as our input is pushing through the input resistor. Since both are the same value, the pushing and the pulling forces have to be exactly equal, just inverted. This means that our output has to sit at -5 to neutralise the 5-volt input one. Now if we ignore the minus sign for a second and check our two input voltages again, we'll see that we've got exactly what we're looking for, a 5-volt output for a combination of 0 volts and a 5-volt input. So it looks like as if our buffer is indeed simply adding the two input voltages together while also inverting them. Is anybody following this? Is anyone out there following this? I'm not following this. I'm not. Op-amps. You know, I mean, this whole series of builds has been full of op-amps, and every time I'm going, oh, it says things and my brain goes, I don't, what is it doing exactly? And there are times when it's sort of like it clicks in and you go, yeah, okay, it's doing that. And there are other times like now where I'm just going, why is any of it what? Non-inverting and inverting bloody things. Okay. So, to verify this, let's assume that input 2 jumps up to 5 volts. then to keep the voltage at the inverting input at 0. So I guess, I don't know. Why does it want to keep it at 0? What is it that an op-amp actually does? So a buffer provides a copy without injecting any current. Now we do have our circuit simulator. Maybe that would be a worthwhile thing to look at. Maybe that will help me at the minute. Let's just have a look at that one. I'm sorry if this is really easy for you people out there. I'm just having a bit of a brain freeze and I just need to, I would really like to understand. So let's see if this is going to help. So are you looking at the right screen? Somebody's telling me something. Oh, War Pigs, hi. How goes the war? Basically, op-amps make their output whatever they can to make the two inputs equal. And one leg is at ground, so the op-amp tries to adjust its output until the inputs are 0. Okay, yeah, that makes some kind of sense. So in this particular screen here, we have two things going in. I don't know why. What's that shifting? Excuse me, why is that shifting about? Okay, so this the shifting about is mirroring the waveform. Somehow they're related. Why are they all related? I don't know, but anyway, this is just we did this bit. That bit's all right. Let's move on. That bit's all right because all it's doing is creating a buffer. It's creating a buffer for a voltage divider, which is finding an average of two signals. Right. Okay. So let's get to the inverting bit again. So this is the inverting mixer, which has this 100k resistor up here. And we're now connected to the inverting input, which gives us an inverted output. That's of no, it means nothing. It honestly means nothing to me today. So the jumper between output and the inverting input gets replaced with a 100k resistor. while we tie the non-inverting input to ground. Then we connect our two input resistors to the inverting input. What does this do and why does this help? First of all, it causes our output signal to be inverted. Okay, don't care about that. To simplify things, we'll again assume that our two input voltages are static at 5 and 0. Now, since we've tied the op-amp's non-inverting input to ground, the output voltage can only stabilize. So what did you say an op-amp is? It wants to make their output whatever they can to make the two inputs equal. So an op-amp is looking for stability, that's what he's saying. Because it's a buffer, it's just trying to reflect what's there. Okay, since we tied the op-amp's non-inverting input to ground, the output voltage can only stabilise if the voltage at the inverting input is nearly 0 as well. So at the non-inverting input it's at 0. So the op-amp is looking to make its own input 0. I don't know why it has control over its input. But anyway, this is because the output voltage depends on the two input voltages. Yes. So an op-amp is a differential amplifier, which means it amplifies the difference in voltage between its two input terminals. So why would it want to do anything? Why would it want to go to 0? Why would it not just amplify the thing that's coming at it? Why not just do its job? Why have a desire to be of a certain state? So it amplifies the difference in voltage between the two input terminals. To do it, it subtracts the voltage measured at its inverting input from the voltage at its non-inverting input. So when the inverting input is larger, that's taken away from 0, which gives you an inverted output. And the result gets multiplied by the gain, which is a very large number, mystery number. Then the op-amp's output tries to set its voltage to the result. If it's outside the voltage range, it will settle on the highest or lowest possible value. And this simple relation gets complicated by the fact we connect the output of the inverting input. We connect the output to the inverting input, thank you, through a resistor. Because then if the output voltage changes, the input voltage will be effective as well. So this feedback loop means that whatever the output is, that affects the inverting input, which again in fact affects the output, which is the nature of a feedback loop. Feedback loop ensures that the voltage at the inverting input is always very close to 0, because if it isn't, the output voltage will adjust until it is. Why? Why will it? Why will it? Whenever the voltage at the inverting input is significantly above 0, the result of the subtraction will be negative. Okay, because you've got 0 at the other one. So if you've got a large number at the inverting one, that'll be taken away from 0. You amplify this, and the output is a large negative number. Gotcha. If the voltage at the inverting input is significantly below 0, the result will be a subtraction. It will be positive, and it will be a massively positive voltage. Yeah, okay. So I can understand it at this point. This means that whenever the voltage at the inverting input tries to go above 0, the output pushes it back down. Why? Why does it try to do that? Why? Why do you say that? I understand if it's a positive signal, it will give a negative output. that's amplified. So are they saying that when you've got a positive input, so if we go back to our diagram, well, it's the same there, the same here. So if we've got a positive input coming into the inverting input, that positive input is taken away from 0, giving us a negative output. That negative output is fed back into the inverting input, which smashes into that positive input that's coming in and reduces it, and vice versa. So you're getting this inverting output. So this is always the opposite to what's going in, but amplified. Is that what you're saying? We say so because of this, this means that whenever the voltage at the inverting input tries to go above 0, the output pushes it back down. If it tries to go below 0, it pulls it back up. They're locked in a stalemate. Because of this, we say that the inverting input is a virtual ground node, simply because it behaves just like a connection to ground, without actually being one. So why is this helpful? We know that the voltages for these 3 points. Again, we don't know the voltages for these 3 points. Why do we? I hate these assumptions. Okay. We know the voltages at these 3 points. 5 volts at input 1. Yes. 0.0 volts at input 2. Yes. And 0 volts at the inverting input. Why? Why? Why that one? Why? How is that 0? I mean, you've just told me that it massively amplifies the signal going through the op-amp, in which case the signal coming back to the inverting input is going to be massive compared to the one that's already there. So if it was, say, let's call it -5 at that point, at the other end you get a gazillion. So you then a positive gazillion. So you then got -5 being added to a gazillion. It's going to still be a gazillion. So now I've got a gazillion going in, which is going to be a negative one. So out the front you get a positive one this time. And that is giving you this kind of massive flip-flop. But I don't see it as being 0. Why would it be 0? It would be massive numbers flapping around all the time. I've evidently lost it. So what are you saying? Over here, you lovely helpful people who help me out of my brain freezes. Just what an op-amp does, yeah. So current doesn't flow through the inputs, they are just sensors. Yeah, I think I vaguely kind of sort of almost grasp that. Change resistor values around and see what difference it makes. I find the circuit simulator the absolute fastest way to understanding of a circuit, much better than breadboarding in my opinion. Well, sort of, but this thing was moving and it didn't make any sense to me whatsoever. Basically, if the positive input is higher than the negative input, the output goes up and vice versa. Yeah, okay. And then because of the feedback, it will balance around the desired output. Yeah, I think I'm getting that. Because the output is inverted, so the opposite of a real because the output is inverted, so the opposite of a real input, so it's forcing it to 0. Because the op-amp makes both inputs the same, but that's why there's a resistor. The input of your op-amp will always be 0. So, sorry about the cap. Sorry, I thought you were really trying to make your point there, Brad. It will always be 0. Well, then why do we plug anything into it at all? I mean, it kind of makes the whole thing pointless. An op-amp stops the circuit from being a voltage divider because the op-amp's input has infinite impedance, no current flows. Okay. Because the positive input is tied to ground, so the op-amp uses the feedback to do its best to get the input to ground as well. Okay, I mean these are all good points. I thank you for all of these. I mean, I kind of get this flip-flop thing. I just don't understand the numbers that are being used. It doesn't. I don't quite understand. So in order to get the voltage at the inverting input down to 0, the output has to neutralize the current flowing through the two input resistors. Since one signal is sitting at 0 anyway, there's nothing coming in that pathway. So we only got to worry about the other one. Our output has to pull exactly as much current through the feedback resistor as our input is pushing through the input resistor. To cancel each other out, yes, okay, I can see that. Since both resistors are the same value, both the pushing and pulling forces have to be exactly equal, just inverted. This means that our output has to sit at -5 to neutralize the +5 one. Yeah, but I thought we had like an infinite large number of amplification. So if we ignore the minus sign for a second and check the two input voltages again, we'll see we've got exactly what we were looking for. I wasn't looking for anything. A 5-volt output for a combination of a 0-volt and a 5-volt. Where are you looking to find this? so it looks like our buffer is indeed simply adding the two input voltages together. I mean, that's all we want. I mean, in some respects, when we get to this point, it's like, okay, just tell me what it does. So it adds two things together. Great. Okay, let's move on. Let's call it an adder rather than anything else. But we'll have a look at the thing again. Is it this one? Inverting mixer. But you know, we're back at this whole business of current and voltage again, which is just nuts. So I'd really like to see that as a value. Or rather than having this as that, is it possible? So at this point, I've got, for some reason, it's exactly the same volts. Can I make it completely different? Can I make that into something else? If we it's not letting me do anything other than that. Okay. No, why is it always the same? Okay. Two different voltages. Thank goodness for that. Oh, that's no help though, is it? Look. So I've now got 3.91 volts. Are you on the right page? Oh, sorry. No, I was on the right one the first time. So I've got 3.9 volts at the top. I've got minus 3.76 volts at the bottom. I don't think that's helpful. And so I've got 0 volts as the out. That's not helpful, is it? I don't know. I don't know what I'm trying to achieve with this. I really do not know what I am trying to achieve. So it's giving me a 9-volt output. I mean a 0-volt output because it's adding these two up all the way along there. Then at some other point it adds up those two, which are the same. So it narrows down at 4 and 4, which then gives me -8. I mean, I guess what we're trying to grasp is, I mean, so what it's saying is that it adds the two waves together, but they just end up inverted, and that's fine. and it's trying to explain to us why that happens. I suppose, but I'm not really getting anything out of that diagram. So anyway, back to the verification. All right, so there's more commentary. This might be good. So because the positive input is tied to ground, the op-amp uses the feedback to do its best to get the input to ground as well, if you say yeah. So the node in your picture will measure minus 2.5, leaving the output at 0. What? The output is a voltage, and the output is a voltage divider. So if we get some voltage at the output, and it happens to be that 2 voltages added and inverted. What do you mean it happens to be? Oh, is it like coincidental? As soon as the negative input gets a tiny bit below ground, the op-amp will start amplifying that difference. Then since the output is connected to the negative, this pulls the input back towards ground. Yeah, no, I sort of get that. Like I say, I get this flipping, that the output is essentially a mirror of the inputs. The inputs added together, that becomes, and then that comes back and tries to pull it towards 0. So I guess what is happening is that you have this variable voltage going in, because ultimately the op-amp, so it seems, is a fascist bastard that wants to be at 0. Everything has to be 0. It has a nihilistic approach to existence. It wants nothing to happen ever. So if you stick a signal into it which is varying, it will want to undo that. So we're sticking a waveform into this op-amp, and we want it to, and so the op-amp generates an output that that is I was on it there for a moment. It generates an output which is the nemesis of what's going into it. That is then fed back to it through a resistor, so that it's not this infinite number of amplification. It's fed back to it in order to try to drag everything back to 0, whichever way it is. Because if it's a positive one, then it will be a negative to drag it back. If it's a negative one, then that will be a positive one to drag it back. So this situation, whether I believe it, whether I have faith in it or not, is what's occurring to allow us to add 2 waveforms together rather than a voltage divider which takes an average. That's why the op-amp's important, because it's reflecting what's coming in. It's because it's generating this. It generates this output in order to destroy the inputs, but that output gives us the combination of those 2 waveforms. That's it. That's what I'm trying to get to. That is it. Right, I think we can all go home. Right. That's what we're trying to do, I think. Yeah, and as you change things, it just makes it work harder. Yeah, fine. So this idea works not just for 2 channels, but you can make it for as many jack sockets as you like. So let's set up a 3-channel version. Ooh, right, okay. So let's do this bit. Let me just see where we're going. Double negative mixer. We want to get to the diode distortion, but we're not doing too bad. So that's got 4 of them. Double negative. Okay. All right. So this bit here. We've got another breadboard bit to lay out. We're now going to take 3 bits, put those together. Let's do this smartly as we can. Let's get back to it. So we need another one of these. So is this in the right place? That's it. That's where it was before. And that edge, yeah, I'm adding another one on this front end. I want to go exactly between on 55. No, I want to go one before it apparently. squeeze that in there. It's going to go to ground. That'll do, not straight, but it'll do. And we want the signal to come out over here. Another smiley face bit. This is a three-eyed monster now. I mean, I hope that's all right. That's not going to work. Come on. Okay, there, like that. I'm going to want another 100k. Ooh, look, there's another sneaky 100k in there as well. So that's quite funny. So this one, I've got 100. Oh, crikey. I've got a lot of 100k. So I've got to take this single one thing out here. Let me get rid of the power in case I do something silly. Take out this fella. So I need 100k to go in there. That's our feedback loop. Cool. That's our 1k. So this 100k goes to that wire. This 100k goes to that wire still, but it wants to sort of move up one, so there's room. Oh, just come on. So all these 100Ks need to go into pin 2. I've not got this right at all. Oh yeah, because this is all based on the. I didn't map out the inverting one. So this has to go to the inverting input like the feedback one has. This then goes to that signal. I need another one to go to that signal. And another one to go to this signal. Now he's done that slightly different. He's brought a, because that's probably not going to reach. That's why. Oh no, that's going to reach. Okay, so that's a bit more visual for me. You've got each of the input signals going through its own 100k, going all in to that inverting input, which also has the feedback from the output to that, and the output is going to the output of this through a 1k. Yes. Meanwhile, I need a ground and a negative. So I've got this pin 4 here is going to negative. I need one to go to ground, which is this one. Yeah, so that's the non-inverting. It's going to ground. Good, 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 good. That's up there. That's all right. Up here, that's good. That's there. That's connected. That's a stupid way to do that. Why not just put another one there? Anyway, so that's good. That's all that done. So once you've done this, check to see if it works properly. All right. I mean, it'll be great if it does, wouldn't it? I mean, I'm assuming. So, as we add more signals, it shouldn't change or something. Anyway, let's put one in. Okay, that seems relatively quiet. Put another one in. Just going to turn it up. So I can't hear it at the moment. So I need to take a third. That's killed it. Right, let's not take that one. Let's take. I'm going to take the pulse from here. There we go. Right, let's plug some power in, shall we? That might help. Or not, that might just kill it. That's why, oh sorry, that's why I wasn't getting any amplification. Right, sorry. But the point is that you're not getting any change in volume as you add them together. Lovely. Cool. On the ball as ever. Good. So it talks about how the output is upside down, which is not really currently a problem for us, because it all sounds the same. But if we were using CV, then of course that would make a difference. So we need to do something about that. So to get rid of the inversion, we invert it again. So we build another one of these buggers into it, do the whole thing again, which flips the whole thing over again so that we have a correct output. I'm not going to build this one. I don't think there's any point of doing that. I think we understand, after we've agonized over this first op amp, which gives us an inverted output of a mix of all three, we can see that adding exactly the same is going to invert it again with no loss of anything because no current's involved. Are you with me? Oh, there's been plenty more talk. Well, I mean, Mr. Jensen 77, I can only go on what I can grasp myself. I mean, I don't know if you're referring to my description or the description in the manual. I mean, to me, because the only information I have, I'm feeding off what's in the manual. So, sorry, don't get distracted. So I'm taking, I'm taking what's being said in the manual, which does seem to describe this process going on within an op amp. Like it's making decisions and it has a will and it has a desire to do various different things. That seems to be evident in the text. This is getting kind of like theology. And I'm taking the text and interpreting it so that I can somehow grasp it myself into what is going on. But the reality is that you've got 2 signals, 3 signals more going in. The output is those added up. Do we actually need to know more than that? Is it helping us understand our circuit design if we comprehend that feedback loop and the process that's going through in balancing out those signals? because in some ways what my brain's trying to do is see everything as zero, and that's actually not the case. None of it's at zero. Well, maybe that one that's tied to ground is, but ultimately in the process of the op amp trying to reduce everything to zero, so it seems, we get this some output. That doesn't make sense, does it? But it's what's happening. It is what's happening. Oh, well, thanks. The one in the manual. Right. Yes, indeed. What do they dream of? But, you know, I think we've got there. I think we have. And I'm not making any of this up. This is true life television of me agonizing over thought processes. This is not me developing a clever way to teach people. Aren't I so clever in the way that I make it look as if I don't understand, and then, oh, a light comes on. Honestly, I was floundering 20 minutes ago, going, I don't even know where to start. So, like I say, we get this bit, I think. So let's move on to adding in some pots. So all we need to do is set up 3 pots as variable voltage dividers. We'll also call them attenuators between our input sockets and the 100k resistors. Well, that looks dead easy. The idea is this. Send an audio signal through a standard voltage divider. We're able to pick up a scaled down version of that audio signal because the voltage has been divided down at the output. The factor by which it's scaled down depends on relationship between the 2 resistors. So a potentiometer sets that relationship. So this is the mixing, this bit here. So we're going to get to a finished mixer thing. So let's do that, and then we'll have a look at the diode distortion, will we? Yeah, because that all happens within this same circuit. So we're going to attempt, look, that's how far we've got to go. Got to go? That's how far we got to go. So, I don't know where that came from. So let's build this bit with the pots, have a look at the diode distortion, build that in as well, and then the job's a good one. So, as I say, we've nearly done it for 2 hours. 2 hours is always a good point at which I feel it would be good to stop. But we rarely do. But I think we could get this. I think we could get this done. So let's breadboard it. Get to where we should be. Right. Focus. I'm going to need another one of these, so it seems. So that's all that's already been in. That's the other one. They put one at the back. Okay. One behind 35. Now we're taking that pin to there. Want 100k. I've got 100k going between those two. That's just 2 lines on the middle 2. Yeah, so that's another feedback loop, because each one of these chips has got 2 op amps. Okay, good. And I got another 100k. These are dropping like flies. Goes from that second pin out to one past. Do I mean second pin, or do I mean, what pin do I mean? Second pin. And this is going out to 29. to jump from the end of this to the other side. Getting tricky in here. This needs to bring that into that top pin there. Yep. I need another 1K. Goes to the end of that one to pin 3 on this side. So now I've got to put these bloody knobs in. So I've got that to that, that to that, to that, to that. That comes over, that comes over, that comes over. Just the 3 inputs. I need that to go to ground. Which is the top one. Down here I've got that either side of a 100k resistor. Got 1k going in there, 100k going out to that, across, then back into pin 1. Yeah, that's all the same, that's all there, that's all there. So I've just got some weirdness going on here now. So I've got these going across. I think I'm going to have to pull these out and see what's going on. So it wants... Ooh, this is going to be tricky. So I've got out 3 of these. So after that, can I go the other way around? Is that going to be more helpful? Not really. Alright, so imagining I'm putting 3 in there, so that works. I've got to put in a tiny little green one. From here to there. And another one which is going past it. 2, 3 to there. Okay, that's still going to my 100k, which is there. And the next one needs to be the same. And that's going to 100k. To there. Then this one needs to be the same again. slightly longer. Not that it really matters. To that one. Which goes to that 100k. Got those two lines going off there. I need something over here. Goes on that third leg. The one in between doesn't go on that one. Let's go one in between. This is going to ground. Yeah. Goes before that. Okay, and then I need to connect that one to that one and that one to that one. Okay. So this needs to connect to there. Also connects there. All right, that's a little bit wonky. There's a little bit of wonkiness going on, but I think that's okay. I think that's okay. Now I've got to put my pots in. There's a pot there. Pot there. There. Should be brilliant. Should be tightly ace. And that goes in. There, that goes in there. I should then be able to adjust stuff. That's an output, so it's these ones here. Woo! Funny that was another one. I'll get this to go into resonance. Hey! Lovely. How lovely. That's lovely. So there we go. That's a proper mixer, that is. It's not difficult. Ugh. The only difficulty is the understanding the nature of components in the universe. That's all. Otherwise, simple. So that's good. That's a little mixer thingy. How awesome. Great. So now let's look at this diode distortion, which should hopefully make the whole thing even more awesome. So it's perfectly usable, yes, but he promised an additional goodie, and that's what we're going to do. It's a really simple and nifty trick. You want to add distortion and warmth to your mixer's output. All we need are 2 diodes, a trimmer, 4 resistors, and another op amp. So from the mixer you get so 100k, which does something. No, so it's the diodes that do a smoothing. Yeah. Oh, excuse me. Through some kind of trimmer. Wonder what that does. Then goes through an op amp. Hooray! Which tries to be 0 at all times and gives us an output of some kind. Yeah, see, we really do understand it. So after our mixer's regular output, we had a 100k resistor followed by a diode going to, and another coming from, a 20k trimmer going straight to ground. Trimmer is set up as a variable resistor, so we can change its resistance on the fly. Then we amplify the result. To understand, first let's assume the trimmer is set to 0 ohms, so as if it wasn't there. Okay, next we'll say the voltage of our mixer's output is slowly rising above the 0 volt line. Okay, the voltage after our 100k resistor will rise just the same, sure. This is because the diodes don't actually conduct below a certain threshold. Oh, okay. So the diodes are kind of putting a slope, putting a glide into it. Thanks, Ken. That's what's going on. The slowness of the diode activating is what smooths off the waveform. Excuse me. So diodes are essentially one-way valves, but to open those valves you need to push against them with enough force. Okay, great. So as long as the pushing is relatively small, it won't be enough to open it, so it will just go through. So as it keeps building up, the diode will start to open, allowing the current to flow, which in turn will relieve some of the pushing force. This effect will only get more pronounced as it pushes even more. So while the voltage at the op amp's output keeps rising, the voltage above our diode will begin to stagnate. So it gets to a certain point and stays there because the diode is letting stuff through. Alright. This is why we need the 100k resistor, by the way, because there's no limit to how far the diode can open. Wow, these things, I mean, components are all about 0 and infinity, aren't they? That's all they seem to deal in. Without the resistor, we'd see the current ramp up exponentially until the world explodes. Since this isn't particularly healthy, we'll use 100k to restrict the amount of current flowing. In this way, the op amp pushes past a certain threshold, the voltage of our diodes will stay constant without anything going up in flames. We call this effect soft clipping. We're essentially cutting off any part of our waveform that's above a certain threshold. Because the diode opens up somewhat gradually, the resulting edge will be slightly rounded, hence the soft in soft clipping. The other diode pointing downwards from the trimmer serves exactly the same purpose, but for negative voltages. This opens up the op amp. It opens up once the op amp pulls hard enough, clipping the lower half of the output waveform. Then we have to buffer the output voltage with another op amp. Since the clip signal is going to be quite low in volume, we're going to give it a fair bit of gain. So replace the straight connection between the output and the inverting input with a voltage divider. Go back to the circuit. So we've got two, yeah, okay, so rather than just having a straight thing going back, and the op amp's upside down, oh my god, it's actually got a 27k and 100k making a voltage divider thingy. I forget what the reason was now. Oh, to give it more gain. This will make it harder for the op amp to equalise the two input voltages and causing it to push and pull with more force. As a result, our clipped output should be brought back to our regular's output volume levels. Fair enough. So it gets messed about with and repaired. Try a sawtooth or sine first. Check the result on oscilloscope. Oh heck. You should see the top and the bottom of the waveform get shaved off. Alright, well we'll see if we can do that. But let's build this thing first. Because this is our last bit. Yes. And let's see if we can get this to work. That will be awesome. It sounds relatively simple. So that's a good thing. So back to the view from above. So these all staying the same. Seem to be, that seems the same. The 1K, that's the same. That's all the same. Doesn't look like anything in that part of the diagram has changed. Excuse me, I'm sorry, I've had it. But we'll get to this, we will. So, let's stick in another op amp. I've got those bits taken out. This goes in pin 21. Yep. So we've got our little trimmer. That's just sort of putting pin away from there. They're out of the way as far as I can tell. It's got one leg. One, two, three. That's in 25. 25 goes to ground. Oh. Duh. Come on, home stretch. So I've got a little one here. Takes those two pins together. I've got 100K throwing itself from looks like pin 2 over here. So from that one, I think so. And the 1K, yeah. This goes all the way to that pin there. That'll leave me 27. That's 10 ohms. 27. Let's knock around the bottom here. That's going from that middle pin into number 2. 20. Good. One last 100K. Between 2 and 3. to a final destination over on 15 here. 1K goes from second pin to the signal on there. That line is going to ground, is it? Yeah. Now, there's another one there, which is that last leg of that. Also to ground? No, to positive. And then finally our two diodes, these two fellas. So we've got one way, goes from the trimmer to that first pin in both directions. So trimmer, first pin, that way. Exactly the same, yeah. Trimmer the first pin that way. That should be it. So let's power my circuit. Let's bring my sawtooth in, and we'll just see if we can hear it first. I don't know what my output is now. Is it this one? Excuse me. It must be, yeah. From the mixer. I'm assuming so. So that must be the output now. I don't know. Oh, that's an output. So I don't want to do that. Well, that's just awesome. And look, the sequencer are affecting other things going on. Well, let's not worry about that. So I've got that. So to do that, I think the output should be brought back to the output level. And the input signal, try a sawtooth, check the result on the oscilloscope. not sure at, if anybody else would like to pitch in, is we've just added this. We've added this one here, which I'm assuming is now the output. We're not getting anything out of it. Done anything completely stupid? Not completely stupid. That's definitely a thing. That's coming from 2. Should it come from 2? It should. Should have that on it. I'm going to try this trimmer. Does bugger all. Okay. Well, let me check my connections. That's plugged in here. So that bit's working. I don't need to worry about that. So I've got one, two, three. So that one should be going to ground, which it is. It's 27k. It's going over to 20, which it is. I've got these two that all both go to pin 1 on there, and the trimmer. Trimmer, there, pin 1. Then you've got this 100k that goes in between the two. Got nothing connected to that one. That shouldn't have anything, it just goes to positive. Got a 1k which goes from that second one to the first one on there, which is that, and that goes to ground. So how is the signal getting into this? That's the next thing. So I've got this coming from where? This big large one comes in from the 1k. Is that the 1k? Yeah. Coming from pin 2, yeah. The earth on the new jack isn't connected. How is it not connected? I've got this here. This here? I can pull that out and put another better cable in. And this line here, yeah. Going to, needs to go to the outside. No, that's not it. Op amp. Okay. Op amp. There's something down here that's not connected. So on that last pin, that needs to go down to negative. That's where the problem is probably going to be. That ain't it either. I mean, it feels like there's wants to be something going on. But I'm making the assumption that that's the output. But I think it is. That seems to be the new output. Forget what this one was for now. But I had that working, and it is working there. Connects that to that. Yeah. It's bound to be a rogue, like this one, a rogue thing I haven't plugged in or plugged in incorrectly. That's the most common flounder. That's going to positive. That's going to ground. These are all connected. That's connected. It's trying to be something. That should not be plugged into that 1K. It should be plugged into the 100K, which it is. Those are the right way round. Oh, well, that is awfully frustrating. Adjust the trim. I know, but trims are another one of these infinity things, aren't they? Where you just keep on going. Oh, look, this fallen over now. It's all going to work when I plug this in. Oh. Which way? Clockwise or anti-clockwise? Well, there we go. Sadly, that's as far as we're going to get with that. If anyone has any bright ideas. The blue one in the top middle looks wrong. Oh yeah, yeah. See what you're saying? Yeah, okay, good. Yeah, saw that. Good, nice. Well done, well spotted. So this one here. That should be going to the ground. Oh, you see, for a minute there. God, just for a minute. Have I got that plugged into the right place now? Should be on pin 1, which it is. Going to the top, which it is. Top, bottom, top, bottom, top, bottom, top, 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 top. Well, that's probably now, probably my inverting output is probably working now. Yeah, okay, so that's fixed that bit, but that was from pages ago. Yeah. Oh look. Okay. Okay, it's burst into life now. Yeah, I can hear that getting rough. Do you want to see it on a scope? So let's take a little something out of there. I can't see. I cannot see. Okay. So as I twist this, we should see the thing change. So let's go back the other way, because we might be seeing is something else. Okay, that's getting worse, because this is supposed to be a sawtooth. So as I'm twisting it, we're getting more and more of a square wave, I suppose. Let's go back the other way, see if I can find the original, more or less. Something like that. And then as we increase the intensity, cool. So that, I think, proves that works, which is nice. Nice and simple, that. Let's see what it sounds like. Quick, although we're going to get more of an idea of this tomorrow when we solder the thing together. So, oops. Let's bring in, let's just talk nonsense for a minute. Let's take CV output, plug that into here. Adjust the trim. Is that better or worse? Try the other way. I've no idea. So let's take let's add another wave in. That just seems to make it quieter. Oh, I don't know. I don't bloody know. How would I know? I mean, how would I know? How would I know? So there we have it. I think, so at the end we got some awesome diode distortion, not really distorting anything. It made things go a little bit quieter and a little bit louder. But according to the oscilloscope, you know, you have to trust the oscilloscope, it did go slightly more bendy. So we do have that. Yeah, ERCAD, we will, all those things, I'm sure. All of those things and more will happen. So there we go. What we will do tomorrow evening then, 7:30, same place, is we will build the module. We will solder it together and then we'll be able to do some proper testing and hopefully properly understand and comprehend the diode distortion. Let's hope so, eh? Because I'm not exactly blown away by it so far. But then it could be for all sorts of reasons. Who knows about the weirdness in my little circuit here. But I felt we did some good work tonight. Something which should be relatively simple, which is actually relatively simple. I got hung up on trying to articulate what op amps were about, and that was difficult but also interesting, and I think we got somewhere. Hi Arthur, I think we got somewhere. And is that going to help us going forward? Well, let's hope so, eh? But maybe the realization that perhaps the understanding of op amps is less important than just saying, oh, it does this, and then moving on with our lives. You know, maybe that's a lesson to be learned. Yeah, no, I think we did enough of that. So what's going to happen next is that we do the soldering. Let's just get to the soldering bit of the, thank you, of the thing. Bloody blah, bloody da. Simples. Good, yeah, yeah. No, that's gonna be good. So tomorrow, as I say, about the same time, we'll kick this off. We will. Ken, I think honestly, we're just learning the same stuff over and over again. Because that's the wonderful thing of being sort of our sort of age, is that bits just fall out the back of your head, and then you can learn them anew like it's the first time and go, oh, wow, that's exciting, I learned something. Then you'll come back to it a couple of weeks later and learn it again, which is great. That's a lot of fun. So yeah, so tomorrow we'll do the soldering. That'll be fine. It'll work perfectly. I have every confidence in it. It doesn't look like a difficult build. Should only take an hour or two, and it's a good one. So there you go, and we're getting there. We are getting there with this machine. This is module number 9, I believe it is. 1, 2, 3, 4, 5, 6. No, it's module number 7. There's 9 in total, so there should be 2 more. I can tell you what they are, just as a little spoiler. To you special 15 people who are watching this, so we have a noise sample and hold module, we have an output module, and a wave folder. That's pretty tasty collection of things for this little system. I think that's going to be good. So 3 more to do, and then it's complete. Which is very exciting. I'm going to put them down there. I'm then going to forget where they are and be in panic next time it happens. So there we go. That's good. So do go and check out my review of the 1222 Performance VCO from Look Mum No Computer. I'm going to be working on the filter tomorrow with a bit of luck. If nothing else terrible happens to me, I'll be working on the filter review, which is fun. The filter is a lot more characterful, I think, than the oscillator. The oscillator is great, and the built-in tuner and things like that are great. It looks fantastic, good, bog standard, does the job, fantastic. With the filter, it's much crazier, much more bonkers, and right up my alley, I think. So that's good. I'm looking forward to doing that one. So cool, that's coming up. That'll be my next video coming up, I think. And then I've got my usual queue of stuff which keeps getting put back every time something new and exciting turns up. Like, for instance, I don't know why I'm telling you like this. This is the wrong live stream for this, but this just turned up. The MIDI cake ARP, which is a perfect timing, because I want to do the Mini Moog Mavis, which I've got sitting over there. I want to do the Mavis, and I want to compare it to the East Beast and the West Pest, and the Dysmobia, the Dreadbox one. Put them all together, and this is a 4-channel arpeggiator, which will be perfect for that. So that's glorious. That's coming up too. But also some of the summer holidays, and that's always going to make things difficult. But don't you worry about that. Let me worry about it. But those sorts of things are coming along, which is great. Anyway, I'm going to go to bed now, because that's enough for me. So thanks ever so much for joining me. That's been super. We got through it again, which is awesome. And I look forward to seeing you tomorrow for the soldering, and we'll go on from there. So thanks. In the meantime, go and make some tunes. Go and enjoy yourself, or go and buy yourself a fantastic jellyfish t-shirt from the merch channel. It's available on YouTube or the website. Go and check us out. Cool. Right. Run VT. I'll push the button on the thing, and we will see you later.